Hello everyone, I am Jaisidh Singh and welcome to our paper SynthProv, Interpretable Framework for Profiling Identity Leakage in WACP 2024. Let us begin by understanding identity leakage, the core of our work. Identity leakage occurs when the identity information of real faces is exposed to a GAN via training and is found to be present in its learned representation. What does our framework SynthProv do? SynthProv detects identity leakage in StyleGAN2 and traces it back to its origins in the training set. Our work identifies the individuals in the training data which suffer a breach in privacy due to identity leakage. Next, we go beyond previous works to analyze this phenomenon in synthetic images as well as in the StyleGAN2 latent space. To the best of our knowledge, our work is the first framework to trace identity leakage. Our work involves approximating identity leakage using image composites created in the StyleGAN2 W space. This is because in essence, identity leakage causes a face to contain identity features of other faces. This can be approximated via latent space interpolation, which captures facial content shared across interpolated latent vectors. By extension, the shared facial content leads to shared identity features. We construct image composites by averaging k latent vectors or via equal interpolation between them. This shares the identity information of the parents with the composite. In our work, we create two types of composites, synthetic and real. To make real composites, we convert real face images to their W representations via GAN inversion and choose k of them as real parents to average into a real composite. This is different from creating a synthetic composite where randomly sampled latent vectors are averaged k at a time, giving a synthetic composite. This is done following the standard inference procedure of StyleGAN2. The data used in our work is created by first obtaining training face images in a set R. We then take a StyleGAN2 model trained on R, which is used to generate a set of synthetic images S. Inverting the real faces to the W space, we choose k of them as real parents and create a real composite by averaging them. The remaining real face images act as real non-parents for that real composite. A similar process is carried out for set S with the caveat of not requiring inversion, as the latent vectors are directly available. This procedure is done for two popular face image datasets, FFHQ and CelebAHQ, creating 10,000 composites of each type for all values of k from 2 to 6. We start our experiments by showing why synthetic composites are better suited for identity leakage analysis. For this, we use the density metric, which is used to evaluate generative models. Given real and synthetic samples in a feature space, density counts the number of real sample neighborhoods that a synthetic sample is a part of. Computing density in the feature space of face matches such as elastic face and arc face shows that the density of synthetic composites is greater than that of randomly sampled images from S. This means that synthetic composites touch more real representations and hence pool more real identity signals into them, making them better samples for identity leakage analysis. Detecting identity leakage. Using our image composites, we detect identity leakage via a quantitative evaluation of identity distances of composites from their parents and from their non-parents. These identity distances are given by a face matcher, which measures the identity dissimilarity between two face images. We find that the identity distances of synthetic composites are quite low from synthetic parents and also from synthetic non-parents. This implies a global similarity or sharing of identities occurring across synthetic images, which magnifies or aggregates into synthetic composites. Analyzing the identity distance distributions of real composites from their real parents and non-parents, we find that they are relatively at large identity distances from their parents and non-parents. This signifies that real identities, which are distinct, are dissimilar from averaged or composite identities. Thus, real composites simply have averaged features of their parents without any aggregation of other identities. We now describe our algorithm or framework to trace identity leakage to its origins in the training data. Starting from a query Q, which is a synthetic composite, we obtain a set of assistants which are synthetic non-parents, highly similar in their identity features to Q, even more so than Q's parents. These assistants act as identity proxies and are denoted by the set A. Next, we obtain the set of latent vectors of the assistants and synthetic parents given by the set QL. This is done to compute identity dissimilarity between the W representations of QL and the real face images in R within the W space. To do this, we first learn a globally identity invariant direction D star. D star is learned by minimizing the identity distances between a reference point and points along certain step sizes along this direction. The process yields a direction which preserves identity information of face representations till large distances from the reference latent vector and needs to be learned only once. Overall, the identity dissimilarity between two latent vectors is computed as the projection of their difference perpendicular to the identity invariant direction T star, so as to encode identity variance or dissimilarity. After obtaining the latent space identity distance of the systems and synthetic parents from the real training set images, we also obtain the face matcher identity distances of these two sets. The distances between these two sets across the image space and the latent space are multiplied element-wise and averaged across the members to give us provenance scores, denoted by SPROV. We use these scores to rank the real faces in the training set to get the leaking reals for the query, which are the real faces leaking the most identity information into it. Observing the distribution of face matcher identity distances again, this time between synthetic composites and their leaking reals, we find that these distances are significantly lower than the identity distances of real composites from their real parents. This shows that leaking real images are more similar in identity to certain synthetic images than they are to their own real composites. This verifies identity leakage in the StyleGAN2W space and shows its provenance. Qualitatively, we can see highly similar facial and identity features across the queries and the retrieved top 5 leaking reels. This is shown for the celeb HQ data. Overall, we see how SynthProv takes advantage of relationships of synthetic images with their latent representations and discovers how identity leakage is encoded in these representations with the help of image composites. Our framework successfully traces leaking identity signals back to their sources in the training data. We hypothesize that identity leakage may be present in more generative models and may vary according to the specific type of architecture or model being used. With this work and conjecture, we hope to inspire further research on making image generation more private and towards generalizable analyses on identity leakage. Thank you.